Alright, let's start sections 3.4 to 3.6. From previous section, as you recall, we could determine the entropy at a specified temperature T, right? To determine it, we needed several informations, such as heat capacities of a certain substance as solid, liquid, or gas, right? Also, we needed information about the enthalpy change during melting or vaporization, right? In addition, we also needed information about entropy at 0 Kelvin, right? We had no information about it, okay? And in this section, we'll define it. That's about the third law of thermodynamics. Okay? We also introduce related properties. And about entropy, the second law of thermodynamics. As you remember, second law of thermodynamics states that during irreversible or spontaneous changes, the total entropy increases always, right? To calculate the total entropy change, we needed to calculate entropy change for the system and also entropy change for the surroundings. And we had to add two of these and check that the total entropy change is positive. That's very inconvenient, right? So, to simplify the process that a certain change is spontaneous or not, we introduce new physical variables called Helmholtz and Gibbs energy, which basically shows us that a certain process is spontaneous or not. Okay? And these two variables also have other physical meanings, so we'll show that. Okay? Alright, let's move on. Oops, sorry. The third law of thermodynamics. So we need to define the entropy at absolute zero. Okay? At 0 Kelvin, we can imagine that all thermal motions of the molecules are quenched, right? There's no motion because temperature is related to thermal or random motion of molecules, right? So at 0 Kelvin, there will be no thermal motions whatsoever, which means that all atoms or ions have perfectly crystalline, perfectly ordered state, right? There will be no disorder, no thermal motion, which indicates that entropy is zero at 0 Kelvin. Actually, the thing is, we cannot really reach absolute zero, but we can simply imagine that at absolute 0 Kelvin, entropy is zero. So we got the reference point for the definition of entropy as a function of temperature. Okay? So this is also called Nernst heat theorem. Entropy change accompanying a physical or chemical transformation approaches zero as temperature approaches zero. That's pretty much it, right? If all the materials, all the atoms or ions are perfectly crystalline state. Okay? Very simple, right? Third law of thermodynamics is very simple actually, right? So basically we define entropy as zero at 0 Kelvin. Okay? Then we can define entropy at any temperatures using this reference point. Okay? Alright. So since we define entropy at 0 Kelvin as zero, the entropies reported relative to this value is called third law entropies, or just simply standard entropies, as we mentioned, standard enthalpy or standard internal energy, etc. Right? And standard entropy is denoted as S naught, okay, as specific temperatures. So for specified temperature for specified material, we can define the standard entropies, okay. And if you have any physical changes, or even for chemical reaction, if we have information about the standard entropy for reactants and products, then we can simply calculate standard reaction entropies like this, as we did for standard enthalpies, right? Same basically, right? If you have information about entropies, molar entropies for reactants and products, you can simply calculate standard reaction entropies. And these kind of informations, we can get it from the tables in the appendix usually, okay? It's very simple, okay? That's pretty much it about the third law of thermodynamics. Let's move on to the next slide. Oh, sorry. Okay. Helmholtz and Gibbs energy. As I mentioned at the beginning of this section, to show that the second law of thermodynamics holds, we need to first calculate the entropy change for the system, entropy change for the surroundings, and we add them up, and finally see and check that the entropy change of the total entropy change is positive. If it is positive, the process is irreversible or spontaneous. If it is zero, then the process is reversible, right? That's very inconvenient, right? So, to make things simplify, okay, we can now focus almost exclusively on entropy change of the system. Treating the surroundings and total entropy is trivial. Even we do this, we only consider entropy change of the system, we can determine that the change is spontaneous or not. Okay? Alright. Let's start from the Clausius inequality. If you recall, consider a system in thermal equilibrium with surroundings at temperature T. Okay? For change in the system with transfer of heat, the Clausius inequality is like this. Remember, right? The S system is larger or equal to dq over T, right? Alright, we start from here. The S minus dq over T is larger or equal to 0. Okay. Okay. Let's consider two different cases. Heat transfer at constant volume. Okay. If the process is at constant volume, here dq is equal to du, right? Okay. Because at constant volume there is no work, no expansion work. Also we assume that there is no non-expansion work. So basically there is no work whatsoever. Okay? In that case, dq is equal to du, right? So this Clausius inequality changes to ds minus du over t is larger or equal to 0. Okay? If you rearrange this, tds is larger or equal to du. Okay, right? Easy, right? So from here, we define a new physical variable called Helmholtz energy, or denoted as large capital A. Here, A is defined as U minus Ts. At constant temperature, if you take the derivatives on both sides, dA is equal to du minus Tds. Okay? Du minus Tds. So du minus TdS is negative if the process is irreversible or spontaneous, right? Claudius inequality is basically same as the second law of thermodynamics, right? It shows that the process is irreversible when this is larger than zero, right? Not equal. When it is equal to zero, which means that this is the reversible process, right? So, if you define a new variable called Helmholtz energy, A, as U minus Ts, if Helmholtz energy change is smaller than zero, if Helmholtz energy decreases for a specific process at constant temperature, then that process is spontaneous or irreversible, basically following the second law of thermodynamics. So simple, we only need one variable, right? If that variable decreases for a specific process, that is the irreversible process. Okay, that's all. Right? Similarly, from the Claudius inequality, if heat transfer is occurring at constant pressure, then dq is equal to dh, right? Enthalpy change. Okay, so if you rearrange it, TdS is larger than dh. Okay, from the Claudius inequality. Now we define a new variable called Gibbs energy, denoted as large capital G. G is defined as H minus Ts. Okay, if you take the derivative at constant temperature, both sides, dg is equal to dh minus tds. Okay, so if dg is negative, okay, which is equal to this condition, and this condition is Claudius inequality, second law of thermodynamics, irreversible or spontaneous change. Okay, so for constant pressure process, if Gibbs energy is negative, Gibbs energy change is negative, or Gibbs energy decreases, that process is spontaneous. Okay? Very easy, right? Okay. So it's basically showing the criteria for spontaneous process. For example, for Gibbs energy, G is H minus Ts, right? So dg is dH minus Tds, right? So not only H or S satisfy the spontaneity, right? Both of them should satisfy the Gibbs energy change. Let's say Gibbs energy should be negative, right? Okay. So for example, even though H, the enthalpy change is positive, right? If entropy change is also positive and large one, then the resulting Gibbs energy change could be negative, right? Resulting in the spontaneous change. Okay? On the other hand, if entropy change is negative for a specific process, okay? Even though entropy change is negative, if enthalpy or if internal energy change is negative also, and with large number, then the Gibbs energy or Helmholtz energy could be negative, resulting in the spontaneous, basically representing spontaneous or irreversible process. Okay. So Helmholtz energy defined as this: if Helmholtz energy changes is negative for a specific process, that represents that the process is spontaneous. Okay, it's very simple. If you look into details about this expression, actually it's same as the second law of thermodynamics, actually. Okay. to simplify the problem, we introduced a new variable called Helmholtz energy or Gibbs energy. And dA is basically du minus T ds. Okay? If you express this like this, minus T over du plus ds, right? Okay. This one is entropy change for the system. Okay. In this part, du, actually minus du basically represents the amount of heat gained by the surroundings, right? So minus du over T basically represents entropy change of surroundings. Right? Okay. So basically, this part is ds surrounding plus ds system total. Okay. Right. So we didn't really want it to do this. Calculate this, and add them up. So we introduced a new variable, okay, which basically represents the same thing, right? Basically same thing. The second law of thermodynamics. Okay? Alright. Same interpretation holds for Gibbs energy too, right? Okay. Oh, alright. Interesting thing about these new variables, Helmholtz or Gibbs energy, is that they not only represent the second law of thermodynamics, or which process is spontaneous, right? They also have another physical meaning. At first, Helmholtz energy represents the maximum amount of work accompanying a process, maximum amount of work which can be done for a specific process. So Helmholtz energy is also called maximum work function. Why? Why Helmholtz energy represents a maximum amount of work? Let's demonstrate it. Right. Let's use the blackboard here. Okay. So we want to show that Helmholtz energy represents maximum amount of work. Why? Okay. Let's prove it. First, let's start with the Clausius inequality. ds is larger or equal to dq over t, right? Okay. So which means that t ds is larger or equal to dq. Okay, we got this. Next, from the first law of thermodynamics, du is equal to dq plus dw. Okay. So from these two, since dq is smaller than tds, okay, which means that du is smaller than tds plus dw if you replace dq by tds, right? Okay, if you express this as a function of dw is larger than du minus tds, right? dw is larger or equal to du minus tds, which means that if the system does work on the surroundings, the W would be negative, right? And the most negative value of the W would be equal to this, right? Okay? If dW is negative, and dW is larger or equal to du minus TdS, okay? And the most negative value of dW with the largest absolute number would be this, right? So dW maximum would be du minus TdS, which correspond to the A, right? Okay? Alright. Maximum amount of work. And this relation only applies to reversible path, right? Okay, remember? We started from the Clausius inequality, so this larger means basically represents the spontaneous or irreversible process. This represents the reversal process, right? So this relation holds for reversal process, right? And you remember that for reversible process we do the maximum amount of work, right? From the chapter 2. Okay? So now finally we show that we do maximum amount of work during reversal process, and that is indicated as Helmholtz energy. Okay. All right. Let's go back. So you can read this slide or the textbook. This basically shows the different cases how to interpret this Helmholtz energy. So if there is a certain problem which asks questions how to calculate the maximum amount of work, then all you need to do is calculate the Helmholtz energy. Okay. To calculate Helmholtz energy, you need information about internal energy and entropy change. Okay, because that's the definition of Helmholtz energy. Same process can be applied for Gibbs energy. Okay, Gibbs energy. The definition is H minus Ts. So dG is dH minus dTds at constant temperature. If Gibbs energy decreases for a specific process, which represents that the process is spontaneous, right? Okay. Similarly to the Helmholtz energy, Gibbs energy also have different meaning. Gibbs energy represents maximum non-expansion work. Non-expansion work. Okay. Helmholtz energy had meanings of maximum work. Okay. Gibbs energy, maximum non-expansion work. Why? Let's demonstrate it. Okay. All right. Let's use the whiteboard again. All right. We want to show that Gibbs energy basically represents maximum amount of non-expansion work. Non-expansion work, other types of work. Okay. Why? Okay. Let's start from the definition of enthalpy. H is U plus PV. Okay. If you take the derivative, dH, du plus dPV. Okay. From the first law of thermodynamics, du is equal to dQ plus dW. Okay. And just leave dPV. Let's assume that the process is reversible. Just assuming. If the process is reversible, you can put just reversible here. Okay. From the definition of Gibbs energy, dg is equal to dH minus T ds, right? Okay. And dH is here, the Q reversible plus the W reversible plus the PV minus T ds. Okay. And if the process is reversible, dq reversible is equal to T. dq reversible should be equal to T ds, right? From the definition of entropy, ds is equal to dq reversible divided by temperature, right? So we basically remove this, right? TdS minus TdS, okay? So dg is equal to the W reversible plus the PV. Okay. Let's put out PdV plus VdP. Okay. Okay. So the amount of work during reversal process can be divided into, first, the amount of expansion work. There are two different, let's say there are many kinds of work, right? First, expansion work and other types of work. Okay? And expansion work for reversal process can be represented as minus PdV. You remember? Okay? And there are other types of work. Okay? Expansion work, other types of work, plus PdV plus VdP. Alright, so let's remove these two. We finally get the WE plus VdP. And if the work occurs at constant pressure, if the pressure is constant, then you can remove this. Finally you get this. So dz is equal to dW reversible for other types. Non-expansion work, maximum non-expansion work. Okay? Gibbs energy represents maximum amount of non-expansion work. Okay. Let's go back. So if there is any problem which asks about the amount of work associated with non-expansion process, then you can calculate the Gibbs energy. Okay? To calculate the Gibbs energy, you need information about enthalpy change and entropy change, or specified temp change or process or reaction. Okay? Finally, as we for specific chemical reaction, we could calculate standard enthalpy change. We could calculate standard entropy change, right? Enthalpy change and standard entropy change. Okay? And by calculating these two, we can also determine standard Gibbs energy for specific chemical reaction, right? Or standard Gibbs energy for chemical can be determined if we have information about standard Gibbs energy of formation for each species, reactants, and products. Okay? These informations can also be found usually in the tables from the appendix, right? For different materials, right? So if you have information about this, standard Gibbs energy of formation for reactants or products, you can simply using this equation, you can determine standard Gibbs energy of reaction. Standard reaction Gibbs energy actually. Okay. Alright. So this is the end of section 3.4 to 3.6. Now we'll move on to the section 3.7. Okay, now we move on to section 3.7 to 3.9, the final sections of chapter 3. Title of these sections are the machinery, okay, as we saw in chapter 2. So we'll see a lot of mathematical expressions and their relations and so on. Let's check the subtitles. Combining first and second laws. So we've learned the first law of thermodynamics, energy conservation, right? And the second law about entropy, right? The increase in disorderliness, right? We can combine these two laws and we'll see very interesting phenomena. Many interesting mathematical or thermodynamic relations between many different variables. Okay, so we'll introduce them. And finally, we'll consider real gases. Okay, and we'll introduce a new concept called fugacity, which is an effective pressure for real gas. Okay, so we'll introduce the definition and how can we use this concept of fugacity to deal with the real gas behavior. Okay, so let's first check the first section. The second law, machinery. Okay, so we have learned two different laws, actually three, right? The second law, the first law of thermodynamics, here as described in this differential equation, right? du is equal to dq plus dw, right? We assume a few things. First, we assume that the process is reversible, okay? And the composition is constant. Basically, we are considering a closed system, okay? And there is no non-expansion work. There is only expansion work, okay? So for reversible process, dW for reversible process is equal to minus PdV, right? We have learned this, right? And from the definition of entropy, for reversible change, dQ reversible is TdS, right? Remember? ds was defined as dQ reversible divided by temperature, right? So, if you put dW reversible, dQ reversible to here, to the first law of thermodynamics, you get new relation. du is equal to TdS minus PdV, which is called fundamental equation. It's very important. It's boxed in yellow, right? The importance of this fundamental equation, the first, is that du, internal energy, is an exact differential. So, even though we assumed the process reversible, since it is exact differential or state function, okay, this fundamental equation holds for every situation, all the time, basically, right? All the time this equation holds. It's true. Okay, du is equal to TdS minus PdV. Okay. Another importance about this fundamental equation is that we basically expressed internal energy, U, as a function of entropy and volume, which was not covered before, right? We could express internal energy as a function of volume and temperature, as you remember, right? But here we expressed U as a function of S and V. That's new, right? It's very interesting. Okay. All right. Then how can we understand this fundamental equation for internal energy? Okay. First, for reversible change, since we assumed it to derive that fundamental equation is basically same, right? How about for irreversible change? For irreversible change, first, from Clausius inequality, we know that TdS is larger than dQ for irreversible change. Okay? How about dW? Let's use the whiteboard here. Sorry. Okay. For dW, so let's write it down again. Fundamental equation for du is TdS minus PdV. Okay. For reversible change, we can easily understand this equation, right? For irreversible change, first TdS is larger than dQ according to the Clausius inequality. How about this part? If you compare reversible and irreversible processes in terms of work, let's compare dW reversible with dW irreversible. If you compare the absolute number, we know that during reversible change we do more work, right? Okay. If you assume that the system does work on the surroundings, then we can remove this absolute sign, right? Since the sign of work is negative, right? Okay. And the reversible work corresponds to minus PdV. Okay. So if you put minus sign here, minus PdV should be smaller than the W irreversible. Okay. So for reversible change, TdS is larger than dQ, minus PdV here is smaller than the W irreversible. Okay. So we can sort of qualitatively understand how this fundamental equation holds for every change, reversible or irreversible. Okay? Alright, let's move on. Let's write it down again. So fundamental equation for the U. This equation basically represents the internal energy change as a function of entropy and volume, right? Which means that, as we did in chapter 2 many times, we can express the rate of change, or how much internal energy changes as a function of entropy as partial derivative, right? So basically, round U, round S at constant volume, right? Yes, plus round U, round V at constant entropy dV, right? So basically, total derivative of internal energy as a function of entropy and volume. Okay? So, which means that this partial derivative round U round S at constant volume is equal to temperature, right? Also, this partial derivative around U around V at constant entropy is same as minus pressure. Very interesting, right? We got new expressions for temperature and pressure, okay, based on fundamental equation. Okay, very interesting. There is another interesting relation that we can get from this fundamental equation that is called Maxwell relations. So let's see what is Maxwell relation. Since this internal energy is a state function, okay, so if you assume, let's move back to the slide number 20, okay, Maxwell relations. So state functions are exact differentials, meaning that they must pass the test that indicate their independence of path taken, okay? Which means that if there is a function f, which is a function as a function of x and y, so we can write it like this: f is a function of x and y, and f is an exact differential, df is an exact differential, okay? And as we did for the fundamental equation, we can write it like this, right, as total derivative, right, same, okay, okay. Then what we can know is that the partial derivative if you do the partial derivative twice, for example like this, you first take the derivative of f as a function of x and then y should be equal to as this, right? If you take the partial derivative twice for the function f by x and y, the order is not important, right? You remember from mathematics class, right? If you take the first derivative by x and y, which is same as derivative as a function of y and x, right? Which means that this part corresponds to here, okay, which is G, right? G here, okay, and this part corresponds to H, right? Okay. So if you apply this relation for this fundamental equation, what you can get is basically you take G, take the partial derivative of G as a function of y, y is V, right? You take G, actually it's not, it should be like this, right? If you take partial derivative of T as a function of volume at constant entropy, which should be equal to partial derivative of minus P S at constant volume, right? We got new relations relating to basically relating unfamiliar partial derivatives, okay? That's called, that's called Maxwell relation. And we get these relations from fundamental equation. Okay? So basically, from the fundamental equation of internal energy, we can get this Maxwell relation. round T round V at constant entropy is same as minus round P round S at constant volume. It's quite interesting, right? Mathematically it's okay, but we cannot really see the meaning of this Maxwell relation, right? Round T round V, round P round S, what does that mean? And the importance of these Maxwell relations is that using this relation, we can do many interesting mathematical derivation that we could not do during chapter 2 or 3, right? We'll get back to that point later, okay? Alright. So we got the first Maxwell relation, okay, from the fundamental equation for internal energy, which means that we can get the same fundamental equation and Maxwell relation for other functions. Okay, which means that so we got fundamental equation for the u first. Okay. The u is equal to TdS minus P dV. If you start from here, we can get other 3 more fundamental equations. For example, the H. How? H is defined as U plus PV, right? Which means that, which is du plus PdV plus VdP, which corresponds to TdS minus PdV plus PdV. So we get TdS plus VdP. Okay, this is the fundamental equation for enthalpy, dH. dH is equal to TdS plus VdP. Similarly, we can get 2 more fundamental equations for Helmholtz energy and Gibbs energy. You can do it by yourself. The result is minus SdT minus PdV. dG is equal to minus SdT plus VdP. Okay. So we basically got 4 fundamental equations. Okay. Basically showing the internal energy, enthalpy, and Helmholtz energy and Gibbs energy as a function of some variables, entropy, volume, or pressure, temperature, etc. Okay. And from each of these fundamental equations, we can get Maxwell relation. We first got from here, we got round T round S is equal to minus P S V. Okay. From this equation, from this fundamental equation, we can get round T round P at constant entropy is equal to round V round S at constant pressure. Okay. From this equation, round S round V constant temperature is equal to round P round T at constant volume. Okay. Vs, right? And from this equation, finally, we can get minus round S round P at constant temperature is equal to round V round T at constant pressure. Okay. So we got 4 different fundamental equations and 4 different Maxwell relations. Okay. All right. Then, as I mentioned, we can use this fundamental equation and Maxwell relations to solve some unsolved problems that we encountered before. Let's see an example. Next slide. For example, if you remember, when we try to calculate internal pressure, IT, remember internal pressure. Okay. The definition of internal pressure was around U around V at constant temperature, right? We try to calculate it for real gas, and we introduced a model system for real gas, which was van der Waals gas. You remember? Right? And we calculated it. We couldn't do it. We couldn't do how. So I just showed you the result. So based on van der Waals gas, if you calculate it, you basically get a V n square, right? We didn't know how to calculate this, but now we can do it using fundamental equation, not fundamental equation, Maxwell relations. Okay, let's see. How can you do it? Okay, let's start from the fundamental equation of internal energy, TdS minus PdV. Okay. And we want to calculate this, right? So what we do is we divide both sides as a function around V and take the constant temperature. Okay. So around U around V at constant temperature, which we want to calculate as internal pressure, should be same as T around S around V at constant temperature. That's here. And if you divide dV by dV, which is equal to just 1, okay. You got expression for internal pressure. And if you look at the Maxwell relation, you can find this around S around V at constant temperature, which is equal to around P around T at constant volume. This one is equal to this. You can find it from Maxwell relation. Okay? It's not possible to calculate this directly, but you can calculate this around P around T at constant volume, okay, easily, based on van der Waals equation. If you recall the van der Waals equation, it looks like this, right? You can calculate this around P at around T at constant volume. Around P around T at constant volume should be equal to nR minus V minus NB, right? Because there is no temperature term here. So if you put this here, you can easily calculate pi t. This one should be equal to, right? Same as here. So we could not calculate it before, but now using Maxwell relation, now we can calculate this. Why internal pressure is positive for real gas, okay? Especially for van der Waals gas. Okay. All right. Alright, let's move on to the next slide. The properties of Gibbs energy. So we got expressions for fundamental equation of 4 different variables: internal energy, enthalpy, Helmholtz energy, and Gibbs energy, right? And especially Gibbs energy is more important than the others. The reason why is that the fundamental equation for Gibbs energy is shown here. dg is equal to vdp minus sdt. Compared to other functions, internal energy, enthalpy, or Helmholtz energy, Gibbs energy is the only function described as a function of pressure and temperature. And as you remember, pressure and temperature is the physical variables which can be easily controlled and measured. So basically, based on experiment, we can measure and we can control these two values. Okay? That's why Gibbs energy is much more important than the others. Okay? So, let's look at more closely about Gibbs energy behavior, how it changes, how as a function of basically pressure and temperature. So dg is equal to vdp minus sdt, fundamental equation of Gibbs energy. So basically this v corresponds to round g, round p at constant temperature. How Gibbs energy changes as a function of pressure at constant temperature. Okay, this one is same as v, and this part should be same as this part. How Gibbs energy changes as a function of temperature at constant pressure, which is equal to minus entropy. Okay. Okay, this means that entropy is positive, right? Entropy represents the disorderedness or randomness. Okay? So, entropy is positive, which means that minus entropy is negative. Okay? Which means that Gibbs energy as a function of temperature, as temperature increases, Gibbs energy decreases. Okay? As temperature increases, Gibbs energy decreases. Okay? Basically, this equation represents this behavior of Gibbs energy as a function of temperature. Okay? And if you compare the entropy of solid, liquid, and gas, gas has larger entropy than liquid, right? Generally. Liquid has larger entropy than solid, right? Which means that the slope of Gibbs energy change as a function of temperature is larger for gas than liquid, larger for liquid than solid, as shown here. Okay, for gas, Gibbs energy decreases has the largest dip, okay, largest slope, negative slope actually, liquid and solid. Okay, so we now know that how Gibbs energy changes as a function of temperature. How about as a function of volume, pressure? Gibbs energy change as a function of pressure is equal to volume. Volume is always positive, right? Which means that Gibbs energy always increases as a function of pressure. As pressure increases, Gibbs energy increases. That's shown here. And generally, volume of gas is much larger than volume of liquid or solid, right? Volume of liquid is larger than volume of solid, generally, not all. But. So, which means that Gibbs energy increases as a function of pressure. The increase is larger for gas, liquid, followed by liquid and solid. Okay? Now we know how Gibbs energy changes as a function of temperature and pressure. Okay. So, although we know that as temperature increases, Gibbs energy decreases, the result is minus S, entropy. Entropy is not something we can easily measure experimentally, right? how if there is any relation or that we can use, we can really experimentally measure to determine the change of Gibbs energy as a function of temperature. That would be great, right? So that relation is given here as Gibbs-Helmholtz equation, which is also very important. We have this, right? E at constant pressure is minus S, okay? Okay. Since, let's use the whiteboard here. So we now want to derive Gibbs-Helmholtz equation, okay? Sorry. Okay. So from here, round G, round T, constant pressure is minus S. And entropy is not something we can easily measure. So, from the definition of Gibbs energy, which is H minus Ts, okay? So from here, S is basically H minus G over T, right? Okay. So we put that here, then we get T G minus H. Basically, we removed S when we replaced it by G and H. Okay? Easy. Alright. If you move this G over T to the left side, what we get is round G, round P, P or T is equal to minus H T. Okay? So we get expressions about round G and round T, and also G over T. And we can get these two variables if we do the if you take the derivative of G over T. Okay? If you take the partial derivative of G over T as a function of temperature, as shown in the slide, you can get expressions here, 1 over T, round G, round T, plus, minus G, 1 over G T squared, right? If you combine these two, you get 1 over T, round G, round T, constant pressure, minus G over T. Okay, you get this expression, right? Alright. So, which is same as minus H over T. So, minus H over T squared. Okay. Means that this part is same as this. Okay. First, let's review. Round G, round T at constant pressure was minus S, entropy, which is not easy to measure, right? So we wanted to replace it by something we can easily measure, right? Experimentally. So by using these mathematical relations, what we got is this partial derivative, G over T. How G over T, Gibbs energy over temperature, changes as a function of temperature, corresponds to minus H over T squared. Enthalpy and temperature, both of them are easy to measure, easy to determine compared to entropy, right? So if you have information about enthalpy and temperature, then we can easily get how G over T changes as a function of temperature. Basically, how Gibbs energy changes as a function of temperature. Okay, by using experimental data. Okay, So this relation is called Gibbs-Helmholtz equation, basically showing the relation between Gibbs energy and enthalpy. Okay, very useful and very important relation. Okay, Gibbs-Helmholtz equation. All right. Now let's go back. Okay. So we got Gibbs-Helmholtz equation, which basically relates Gibbs energy and enthalpy. If you review the Gibbs energy change as a function of pressure, so basically pressure dependence of Gibbs energy, which was same as volume, right? Remember? Gibbs, if you record here, okay, right? Gibbs energy change as a function of pressure corresponds to volume, right? For solid and liquid, first, basically volume change is very small, right? If you do anything, if you change the pressure, volume of liquid or solid does not change much, right? Very small amount, right? So in that case, Gibbs energy change as a function of pressure for solid or liquid is not so much. We can just neglect it. So we don't really need to worry about Gibbs energy change as a function of pressure for solid or liquid. But for gas, it changes a lot, right? For gas, it changes. Okay. So how can you calculate the Gibbs energy change of gas as a function of pressure? It's very easy actually, since round G, round P was volume, right? Okay. So all you need to do is integrate volume. Okay. So for example, if you want to calculate Gibbs energy change as a function of pressure between PF and PI, okay, for ideal gas, let's say, so Gibbs energy change from PI to PF, molar Gibbs energy actually, should be same as integral V volume dP, right? And volume, molar volume of ideal gas corresponds to RT over P, okay, right? So you can simply just take the integral of RT over P, which corresponds to RT log PF over PI. Very simple, right? So Gibbs energy basically changes as a function of pressure based on this relation. RT natural log PF over PI. Okay. So, for example, if we set initial press PI as P naught, the standard pressure, such as 1 bar, right? Then you can get this relation, right? So basically we set a reference point for the initial pressure, right? Then you get this kind of relation. Gibbs energy at a specific pressure P should be equal to standard Gibbs energy at standard pressure 1 bar plus RT log P over P naught. So here P naught is standard pressure, okay, such as 1 bar, right? So you can get the expression for Gibbs energy at a certain pressure. Chemical potential. Chemical potential is a new concept. Actually, we just introduced the definition of chemical potential in this chapter, and we'll see about this chemical potential in chapter 5 and 6 much more. So let's first introduce and define what chemical potential is. Okay? So chemical potential, denoted as Greek letter mu, of pure substance is defined as mu is equal to round G round N at constant temperature and pressure. Up to here, we didn't really care about N, right? We always assumed constant composition, closed system, right? So we really didn't worry about this number of molecules, okay? But if you change the number of molecules of the system, if you change the composition of the system, Gibbs energy changes, okay? So how much Gibbs energy changes as a function of composition or as a function of number of moles is called chemical potential. Okay? And chemical potential is a very useful variable to calculate many things. We will get back to that point later in chapter 5 and 6. Okay? Alright. Especially for pure substance, if there is only one substance, okay, then Gibbs energy, G, should be equal to N times Gm, right? Number of moles times molar Gibbs energy, right? Since there is only one substance, okay? So chemical potential should be equal to molar Gibbs energy. Very simple, right? If there are many compounds together, for example, in a mixture, then it gets much more complicated. But for pure substance, chemical potential corresponds to molar Gibbs energy. That's it. Very simple, right? So, if you write this relation down again in terms of chemical potential, you can write it here, right? Chemical potential at a certain pressure is equal to chemical potential at standard pressure plus RT log P over P naught. Okay. Very simple. Right? So we got this relation. Okay. One bad thing about this expression for chemical potential at a certain pressure is that, for example, if you plot chemical potential or molar Gibbs energy of a pure substance as a function of pressure, okay, if pressure approaches zero, okay, since it is inside of this log, right, molar Gibbs energy approaches minus infinity. That's not very useful. Okay? If a certain variable approaches minus infinity, that's not very useful mathematically, right? Okay? So we need a new concept or new variable which is much more useful in terms of mathematics, which is much more easier to deal with. Okay? That is called fugacity actually here. So let's move on. Real gases and fugacity, the final section of chapter 3. Okay. So we saw these relations here, and this relation holds for perfect gas, right? Because to derive this equation, we assume that the gas is perfect gas, right? Mu is equal to mu naught plus RT log P over P naught. Okay. For real gas is different from ideal gas, right? Everybody knows that. Okay. So the change of molar Gibbs energy as a function of pressure is also different for real gas and for perfect gas. Okay. Perfect gas behaves like this, basically follow this equation log, right? But for real gas, it's a bit different, right? Okay. So the truth is that to describe the behavior of real gas, especially change of Gibbs energy as a function of pressure, we cannot use this equation, right? This equation is for perfect gas. Okay? For real gas, we need new equations, which, as we can imagine that equation would be much more complicated than this simple equation, right? Because it is real gas. There are a lot of molecular interactions and so on, right? Okay? You need new equation to describe real gas. And that new equation would be much more complicated than this simple equation. Okay? But what if we want to use this simple equation to describe the behavior of real gas? We just want to. Instead of using much more complicated mathematical equations, we just want to use this simple equation to describe the real gas behavior, especially Gibbs energy change as a function of pressure. Let's just do it. Okay? We just use this equation. Okay? Basically, this equation. Okay? To describe real gas behavior. But the pressure of real gas is different from the pressure of ideal gas, right? You remember, for example, like compression factor and so on, right? So we cannot really use the pressure of perfect gas. Instead, we use different pressure to describe real gas, which is called fugacity, denoted as F here. So fugacity is basically an effective pressure of real gas. To use this simple equation to describe the behavior of real gas. Okay? Real gas, let's review. Real gas and perfect gases are different, right? They have different volumes, right? For example. So that's why we introduced the concept of compression factor, remember? Right? So, but to describe real gas, especially Gibbs energy change as a function of pressure, we really don't want to use very complicated equations. Instead, we want to use these simple expressions to describe real gas. To do that, since there are differences between perfect and real gases, okay, we need new variable which can replace the perfect gas pressure. So that's called fugacity F. Okay? So we basically can use this equation by introducing new variable called fugacity. Okay? And that fugacity is an effective pressure, okay, which is different from the pressure of ideal gas. Okay? All right. You can just read this slide. So, since fugacity is an effective pressure, which is different from ideal gas pressure, we can express that difference between ideal and real gas pressure using this kind of relation. Okay? Fugacity and pressure here. So this constant pi basically represents the difference between F and P, real gas and ideal gas. Okay? And this pi is called fugacity coefficient. Okay? So if you put this F into the original equation, then you get this equation, right? Mu is equal to mu naught plus RT log P over P naught plus RT ln pi. So these first two terms basically represents the ideal gas behavior, right? And this third term represents the difference between real gas and ideal gas, right? Okay. All right. And one thing we can easily imagine is that as P approaches zero, as pressure approaches zero, which means that gas basically behaves something like perfect gas, right? Then fugacity should correspond to pressure, right? Because it is ideal gas, okay? Which means that as pressure approaches zero, fugacity coefficient approaches number 1, right? Because these two variables should be same, okay? Another important relation that we can derive from here is that, remember that fugacity basically represents an effective pressure of real gas, okay? And real gas and perfect gases are different, okay? For example, in terms of volume, and that difference in volume was denoted as compression factor, right? And interestingly, this fugacity coefficient, which represents the difference between real gas and perfect gas, can be calculated using this equation. And in this equation, what you can see is Z, compression factor. If you have an information about compression factor, you can determine the fugacity coefficient. Okay? That's very important. Okay? Important and also interesting relation. So if you recall, compression factor was defined like this, PV over nRT, right, for real gas. Okay? So let's derive this relation. All right. Okay. So let's derive the relation how we can calculate fugacity coefficient. First, for all gases, for real and for perfect gases, for all gases, we can have these relations. Molar Gibbs energy change as a function of pressure from P to P prime, which should be equal to integral from P naught P prime to P molar volume dP, right? Okay. Which for pure substance should be equal to mu minus mu prime, and also same as RT log F over F prime for all gases. Okay, so F is on fugacity at pressure P. F is a fugacity, and F prime is a fugacity at pressure P prime. Okay. So for all gases, we get first equation, and for perfect gas, okay, we can express this similarly. Okay. So P prime we perfect, same integration should be equal to mu perfect gas minus mu prime perfect gas, which is equal to RT log P over P prime. Since it's perfect gas, now you can use P instead of fugacity, right? Okay. This is equation number 1. This is 2. Okay. If you take the difference between these two equations, okay, what you get is integral p prime p Vm minus V perfect m, here dp, corresponds to RT, okay, log f prime f minus log p f prime. Okay. All right. If you rearrange it a bit more, if you divide both sides by RT, you get T here. Okay. Let's say that P prime approaches 0, basically. Then the gas behaves like perfect gas, right? If P prime approaches 0, then F prime, the fugacity at this pressure, approaches pressure, right? As we saw before, right? Okay. So, if P prime approaches 0, P prime approaches 0, okay, then F prime approaches P prime, F prime approaches P prime, so basically you can remove this, okay, then what we get is log, what is it, F over P, okay, and by definition F over P is equal to pi. Okay. Okay. And this volume difference here, molar volume of real gas minus molar volume of perfect gas, okay, corresponds to P over RT Z minus 1. Okay. So if you put this in here, you can get the relation, the original relation, as you saw in previous slide. Okay. If you have an information about compression factor, you can calculate the fugacity coefficient. Okay. All right. Let's move on. So let's summarize about the fugacity. So fugacity basically presents the behavior of real gas. And if you recall, the difference between real gas and ideal gas in terms of molecular interactions, attractive interaction and repulsive interactions, right? So, for example, in terms of pressure, at moderate pressure, when attractive interactions are dominant, compression factor Z is smaller than 1, okay? And from this relation that we have just derived, since Z is smaller than 1, this part is smaller than 0, right? Smaller than 0. Okay? Which means that fugacity is smaller than pressure. and chemical potential at pressure P is smaller than chemical potential at standard pressure. Okay? Excluding retraction dominant cases. On the other hand, when the pressure is high, when repulsive interactions are dominant, compression factor is larger than 1. Remember, right? And from this relation, since Z is larger than 1, this part is larger than 0, positive, okay? Means that viscosity is larger than P, or chemical potential at pressure P is larger than chemical potential at standard pressure. So basically, repulsion is dominant. R equals 1 to driven apart. Okay? And you can find the supplementary material about viscosity, and especially that supplementary material shows how to calculate the viscosity, especially viscosity coefficient for real gas. Okay? And a model system for real gas is van der Waals gas. So basically, using van der Waals equation, you can calculate the viscosity coefficient here, and you can see that for van der Waals gas, this relation holds when attraction or repulsions are dominant. Okay? So please calculate it by yourself. Okay? All right. Okay, so I mentioned you do your calculation by yourself for the determination of viscosity coefficient for real gas, especially for van der Waals gas. Let's do it by just together. Okay. So we start from the relation between viscosity coefficient and compression factor. Okay. So we'll start from here to determine this and to show that this is really positive when the pressure is moderate, and if that is really actually it's the opposite. If this is really positive for repulsion dominant case, and if this is really negative for attraction dominant cases. So we'll consider this for van der Waals equation. So using this equation, we'll calculate this. Also, let's consider two different cases. First, when A is 0 and B is positive from this van der Waals equation. So A is 0 means that we are not really considering the attraction dominant attractive interactions, right? We only consider repulsion or molecular sizes itself, right? So if this is the case, then compression factor Z, which is defined as PV over T for real gas, okay, corresponds to, since A is 0 here, okay, so PVM actually, PVM over RT should be correspond to VM over VM minus B, right? Okay. And Z minus 1, here Z minus 1, should be equal to over b, right? So velocity coefficient natural log pi should be integral from 0 to p b over vm minus b p dp. Okay, right? And p times vm minus b, here p times vm minus p is equal to RT, right? So p RT b dp. Okay. And since this integration is a function of pressure, R, T, B, all of them are constant, right? So it's simply bp over RT, which is positive. Okay? Simple. Natural log is positive. When A is 0, we do not consider the attractive interactions, and B is positive. We only consider the not really repulsion, the molecular size itself, right? Simple, right? How about the opposite case? Okay, just review this part. Okay. Let's start again. The second case, when A is positive, we consider attractive interactions and we ignore B. Okay, so basically we ignore this. Okay. It's a bit more complicated than the previous one. Okay. Alright, so compression factor Z, PVM over RT, from this equation we can get 1 minus Vm over A over RT. Okay. And if you multiply P over RT on both sides, numerator and denominator, which means that 1 over A m times P over RT. P over RT, the same variable. Okay. Then what you get is 1 minus RT PVM is Z, okay, minus CP. Here we introduce a constant C here, C. Here C is defined as RT square over A over RT square. It's basically constant, right? At a specific temperature. Alright, so if you rearrange this equation, you finally get Z square minus Z plus CP is 0. You get quadratic equation. Okay? So to solve this, you can use quadratic formula, right? So Z is equal to 2 on plus root 1 minus 4 CP. Okay? And Z minus 1 should be equal to 2 root 1 minus 4 CP minus 1, okay? Because we need expression for Z minus 1 to use this integral. Okay? Alright. Now we just put this in here, okay, and do the integration. Okay, so let's just please write it down, or you can just look at the supplementary material. If you put this here into the integral, what you get is integral P0 but 1 minus 4 Cp minus 1 2P dP. Okay. Alright. It's not easy to do the integration just by itself. So to remove this expression, we use Taylor series basically. Okay, so root 1 plus x, basically corresponds to 1 plus x minus 8 x squared, like that. Okay, we can do the Taylor expansion. So if you take this minus 4Cp as x, you can easily get this integral to P over something. What you get is minus C plus P over Cp squared plus blah blah blah, something like that. So basically what we get is minus sign here, okay? And C was positive, you remember? C was defined as RT squared over A, so, right? So whole integration is negative. That's all what we wanted to determine, right? When there is an attractive interaction, when A, Van der Waals coefficient A is positive, the resulting fugacity coefficient is negative. Okay, that's what we wanted to determine for real gas, especially for Van der Waals gas. Okay, all right.